All right, so this is what they look like. This is as easy as an application as you can come up with. So I made this particular example called the fundamental 4, and we're gonna go fire up FLAC2D and we'll go through this project just to kind of get an idea of how these are set up. I built this as a reoccurring test. Every time we build the code, this particular model is ran, and if the results are different, then something's wrong. But it's kind of a nice example. It shows we have beams basically in this drawing. This is typically what I've always seen beams used as. Cables are acting as basically a reinforcement within the soil. Piles here are on the outside of our trench, and then they're basically driven into the soil itself so they can withstand the bending of the soil that wants to fail into the trench. And then liners, lastly, I'm just showing here as kind of the idea of a shotcrete liner along the tunnel. So these are the 4 main ones. There will be more once FLAC2D is grown or developed further, but these are probably the fundamental ones I don't need in any application. Okay, so oh shoot, right here. Ignore that. Simple 7. In FLAC3D, we have 7 structural elements, and I've been using that PowerPoint to make mine. So something I missed a few things, so I apologize for that. So we're going to run this particular model, and all it's showing is how these structural elements help support the soil. So you can see over here on the right of this model, there's no structural support via structural elements. So there's quite a bit of deformation going on at the walls of the trench. Adding the structural support, you can see how it helps that problem. Same over on this side of the model. This has no liner on the ceiling. This one does. The deformation is much reduced for over here. And this is a kind of a side note. You can create here. I just created 2 models. These aren't like 2 separate programs, and I'm just putting in the picture together. These are actually 2 different models separated, but you can do that exact thing as long as your boundary conditions are set. And so it's an easy way to run multiple models without running the program twice. Okay, so I'm assuming you guys are all familiar now with all the stuff on ShareFile. So I'm gonna have you guys download, I think it's called fundamental4.prj, and the data file run.dat. Let's fire up FLAC2D. Okay, so I'm going to open a project because I already had the project file there for you. Okay. Where are you, desktop? I know you're here somewhere. Sorry, I'm kind of a Linux guy, so I'm struggle with Windows. Come back. Oh, into OneDrive. There we go. Okay. Fundamental 4 project. Okay. I apologize for this. So if you get this warning, it's just saying, well, we can't open this data file called test.all SEL's fundamental4.dat. I renamed some of the stuff in here, so it's like it can't find it. That's okay though. All right, so open up the project. Now let's open up our data file. So you can see these are used to be the name of it, but that's not anymore. So open run.dat. I'm just gonna take you out for a minute and we'll make sure we can see a lot of this. And at the end, we'll kind of do more of with the example, instead of just doing a line by line thing, which can get a little monotonous, we'll actually type it in. Actually, we'll go to the documentation, copy it, and then paste it. Okay, so, oh wow. I wonder if I forgot to give you guys this grid. I bet I did. Hang on, quick fix. SEL grid, there you are. And now to give it to you guys. All right, upload the file. My apologies for that. You guys see it yet on your file? So if you just want to copy that file to your working directory, wherever you copied everything else. And that grid, that's a grid file, F2GRID. It's basically, I made the grid in Sketch and then I saved it as a grid file, basically so I don't have to keep going back and making it in Sketch. All right, so let's just run through this. There might be a couple of things in here that you guys haven't seen yet. For example, zone face skin. Has Andre talked about any of that, about skinning in a model? Say, I'm thinking not. It's basically it's a way to assign groups to just the boundaries of your model, and it assigns them automatically. But a better way to understand it is actually doing it. Okay, so I'm just gonna run what I have highlighted here, and I don't know if Andre explained that you can run your highlighted text just by Control-Shift-Execute, or this little button here, execute the selected commands. Boom. A lot of times I'll go back between the console and hiding it because the console will always tell you the information that you just ran. So yeah, basically I imported a bunch of zones, which we can take a look at. So let's look at our plot. And here you go. So another thing, looking at strictly plots is definitely kind of an older mentality we have. The better way to look at your model and actually kind of query things, it's the model pane. So I'll go there. And the model plane is definitely better for seeing these things, whereas plotting is more for looking at histories and stresses and that kind of thing. The model plane gives you a better idea of your model. Okay, so I made this in Sketch. It's very similar to the image I just showed you guys, where we saw the displacements and the deformation with the structural elements and the trench, and then the ones with the tunnel. And then when I issued that command right here, zone face skin, basically what it says, it's found 416 surface faces found, 8 surface face collection found, 416 surface faces assigned, and names in the slot skin. basically what it does, it goes through your entire model. It looks for any free surface, and a free surface in this case would be any zone that has a face that's not touching another zone. And it assigns names for all these faces. The way you can look at that is over here in the control panel. Right now I'm looking at zones. You switch it to the zone faces, it'll just show you the faces. Had I not issued that zone face scan command, nothing would show up here. And this is nice because basically when you're ready to assign boundary conditions, you have all your boundaries here identified by a different group, which is written right here. So skinning is the slot it's put in, and then the group name has been given as east west, top east west. We use it all the time. It's just the primary way to distinguish groups of objects, whether it's for boundary conditions, whether it's for extracting material. Groups are just the bread and butter for that. Okay, let's go back to run.dat. Okay, so skin the model. Now these next set of lines are something I'm pretty sure you've seen before, hopefully. We're just gonna assign a constitutive model to everything. We're gonna assign the properties for that particular constitutive model. Young, Poisson, density, friction, cohesion, tension. All right, so I'm gonna just run those few lines. Done. Let's see what it said. Yep, so property Young assigned to all these things, blah, blah, blah. It's all good. If something went wrong, we'd be getting an error message colored in red. Okay, the next thing I'm gonna do here is assign boundary conditions. So these 4 lines basically take advantage of me scanning the model. So you remember if we go back to the model pane and I clicked on the zone face, all these boundaries here were given a name. East 1, west 1, top 1, blah, blah, blah. And that's exactly what I have here. So I'm going to apply a velocity, normal velocity of 0 to those particular boundaries. This has become the kind of preferred way of assigning boundary conditions to your model. There's actually numerous ways you can use a zone grid point fix and zone grid point initialize. Basically, it does the same thing. But this has become kind of the ideal way of assigning boundary conditions through face apply. Okay, so next we're gonna add a little gravity to this model. Side note, when you say model gravity, you don't always have to put in the vector. It will always take whatever number you give and assign gravity in the y direction, unless explicitly told not to. All right, so I'll run these 2 lines. It basically initializes the stresses in the zones based on the density and gravity. It's a convenient way of you not having to cycle to come to that initial state. All right, and then these next 2 lines, the first one you've been told about. So every model, whether it's in FLAC2D, FLAC3D, PFC, anything, any of our code, you have to specify whether it's large strain or small strain. So this is small strain, so large strain is set to off, to false. And we're gonna do then a model solve because we have our zones, we have boundary conditions, we have a constitutive model, we have gravity and density. These are all things we need to solve the model. And what are we going to solve to? We're going to say a convergence criteria of 1. Okay, so it's going to take a little bit of time. There's quite a it's not converging, which is very interesting. I wonder if I meant it to do that. I bet I did, because the one's unsupported part, it shouldn't converge. Okay, that's fine. So instead of that, we're just gonna go cycle like 1,000. And I'm just gonna throw a return so we can stop there and look, see what's happening. Okay, this is good. So you run into problems and you have to figure out what's happening, even though this is like a test that's repeated thousands of times and isn't supposed to do that. All right, that's fine. Let's look at the plot. So I just double clicked on the plot. One way you can just kind of see if the model is converging is this contour. So click on the zone. Right now it's colored as displacement, small displacements. That's good. And then we're going to color a contour by zone value of convergence. Looks like it's converged to me. Ah, okay. I definitely, when I first went through it, I must have missed a couple lines. My guess is I probably missed a boundary condition. Okay, so it does converge, which makes sense because that's how I had initially made this example. I have a feeling I just missed some lines. Anyway, okay, so going back to the end of the solve convergence, let's take a look. Remember convergence 1.0, so there shouldn't be anything greater than 1.0 in this plot. Okay, so it's converged. Okay, let's continue on, and now we're gonna do a little bit of excavation. So another kind of nice thing about, oh, actually, I think, never mind. When I made the grid in Sketch, I actually grouped these different blocks where the trenches are and where the tunnel is. Just gave them unimaginative names of block 8 through 10, 11, 14, and 15. So basically, we're going to do an excavation, which this is not the way you actually excavate material. I think Andre might have brought up the zone relax command, zone relax excavate. That's the proper way to do an excavation because it actually reduces the properties within that excavated region and the forces gradually instead of just all of a sudden blowing them out, and then you'd have spurious dynamic effects, which drastically changes your model's results. So we'll just delete those. I'll run lines 27 and 28. Let's take a look back at the plot. And they're gone. Quick and easy excavation. All right, so let's get into the actual reason we're here for these 2 hours. This is the way you create structural elements in the data file. So I said there are some ways in the model pane. They're pretty they're not very well put together right now, we'll say. So we're just going to stick with how to make structural elements in the data file. And the easiest way is just structure create by a line. There's other options, but they're the ones I'm putting in are all linear. And then the way to specify the number of segments is through segments. So let's run these few lines. Don't worry about this, and you might even get a pop-up saying, oh my gosh, node 12 does not have a link, node 13 and 14 don't have links. In the pop-up, you can say ignore, I think. It's not an error, it's just a warning. Because typically when we're running these models, your structural elements are interacting with the grid somehow. We don't, and these particular nodes are not doing that. In fact, I think we're going to get rid of that warning. Okay, so I will take a look at my model pane. Oh, and they added them, the 3 beam elements. Right there. All right, and just continuing on. All right, and then I won't go into this. This is basically the same thing, but now we're making cables. And sorry, I haven't. The hotkey for executing your selected commands is Control-Shift-E. And lastly, we'll throw in a couple files. Okay. And now let's turn our attention to some liners. How do we, make curved structural elements? And here's one per particular case. So we have our tunnel over here that we want to basically get some structural elements on. We're trying to make a concrete liner, right? You could, and people do this, you go through this model use fish or something, find every single grid point, and then you could basically do the same thing I've been doing for the other structural elements, like make an element from here to here, one segment, here to here, one segment, here to here, one segment, all the way around. That'll take forever. So instead, what I do is I am going to identify a face group. Zone face group is going to be a group of faces at a particular location in my model. So we'll run this particular line. So what it's saying is, it says find any face within this range. The range logic, using ranges, used all the time because it basically specifies where in your model, what in your model, that kind of thing. And these numbers basically from X and Y, basically I'm just telling it to find any faces within this little box here. And you just have to trust me, the numbers are right. Okay, so from that command, it did group tunnel right, added to 28 faces and slot default. And I got really precise with the range. In fact, I didn't include any of the faces down here. Because in this example, the shotcrete's just going to be applied to the walls and the ceiling. So let's take a look. Okay, so now let's get rid of our beams and our cables and our piles. And right now we're just looking at zone faces. So remember when I skinned the whole model, those are all in here. So I am going to hide those. Let's see. And the way to do that is, so we're looking at all the faces, any face. I'm going to restrict it to just default. The default slot is because I didn't specify a slot when I made this zone face around the tunnel. Go. Interesting. That it would just hide all the skinning ones or just show the default ones. Apparently not. Okay. Regardless, this is what we made right here. This blue face. And you can see right here, it's called default equals tunnel right. Tunnel right is what I called it. And the reason we did that is because now we have a group of faces that we're going to apply this liner to. And the way we do that is with this particular command, structure liner create. You'll kind of notice a trend here. It's structure cable create, structure liner create. That's how we create things. But the advantage here is now I'm going to say I want to create this liner by zone face. Well, what zone face? I made it. It's called group. We're going to put in range group tunnel right, which I just made above. Execute that. Good. 28 elements, 29 nodes, 29 links created. This one's happy because it made it linked successfully to a zone in the model. And there it is. So let's hide the zone. You can see it made it right there. Well, they get small. Okay, cool. All right, what else do we got? Structural length, tolerance, contact. Okay. I don't think this command is entirely necessary. The reason I'm adding it is it's important to, when you know you've made like 10 elements and say I have 11 nodes, it should say, okay, if you know that the whole element is within your soil, within what is inside zones, I should have 11 links. Sometimes that doesn't happen, and it might spit out, oh, you only have 10 links out of the 11 created. And a lot of times that was kind of the motivation of this this warning, was that, oh, there's one node that's not linking somewhere. Are you sure you know about that? And basically what's happening is the linking logic is looking for a zone that's closest to it. And long story short, sometimes it fails and then it can't find a zone, and then it just won't create a link. You can change the tolerance to say, okay, look a little further for a zone that's you're close to. And then that's how we change this tolerance with this command. I'll just run it since it's there, but I don't think it's actually necessary. All right, cool. So now we created the geometry of these structural elements, much like how we create the geometry of zones. Now the next logical step will be to assign these elements properties. And each property is explained in detail in the documentation, which, let's see if I can just pull up real quick. I'm just going to the online documentation here. I don't know why I can just prod it up from inside the program. Okay, so as I mentioned previously, ITASCA software guide, structural elements. Let's take a look at beam properties. We want to know all the properties with the beam. You'd think, yeah, I'll click on beam structural element, but no, it's in beam type structural elements. Kind of a little confusing, in my opinion, but beam type structural elements are beams, not cables, beams, piles, liners, beam type. So we can look at all their properties, and they're listed here. Cross-sectional area, density, and what's this direction Y? I won't get into that, but it's another property. Moment of inertia Y and moment of inertia Z. Oh, that's weird. Just keep in mind, some of these are 3D only. Moment inertia for us, 2D only, is just MOI. So when you're looking at these properties, you might run into that a couple times, that, oh, this is actually a 3D only property. Rather than going line by line through all this, just know that, okay, we made beams, we made cables, we made piles, we made liners. We're going to assign all their properties. Properties include element specific, Young's modulus, and Poisson's ratio. And then also the properties include how it interacts with the grid. So that will be pretty much anything that has, for cables, grout, for piles and liners, anything that says coupling. And you can see there's a lot of different coupling parameters. So for example, this coupling stiffness normal. So that's the stiffness in the normal direction, and we'll talk a little bit more about that later. And then there's also going to be stiffness in the shear direction. So all these properties, there's a lot of them we're going to assign, right, with these commands. Oh, good. I don't think I did not grab this last line here. There we go. All right. One thing that popped up here is that it's saying liner property Young's modulus is automatically divided by 1 minus nu squared to count for plane strain conditions. This is one thing that distinguishes a liner from any other element type, is that whatever Young's modulus you put in for that element, it will automatically divide it by 1 minus the Poisson ratio squared. And that basically is saying where this liner is not going to be treated as a single element, it's going to be treated as an element that is continuous out of plane, which is typical for what a shotcrete or any kind of liner is. So yeah. And then here, I'm just going to initialize the grid point displacements to 0. Because you'll remember we solved previously and displacements were very small, but let's just make them all 0. We're going to add in some damping. Pretty much all models that you run into will be damped in some capacity. And I think you talked about damping yesterday. Local dampening, combined damping. And then when you talk about dynamics, there's a different kind of damping for that. And for the structural elements, there's basically local and combined local. And really either type here would work fine. I'm just using combined local because most of this motion is going to be uniform in the vertical direction. And I'm just going to cycle for 1,000 steps. This particular case, if I said solve convergence 1, it would never converge because we have that one trench, if you remember on the far right, that had no structural support, and it would actually just fail, given the condition or given the properties that we assigned it. Okay, so we'll just cycle 1,000 times. And now I'm going to switch to my plot because here we can actually see a lot of good things like displacements, stresses, and that kind of stuff. So as I had shown in that PowerPoint picture, this just kind of highlights, oh, there's no structural support, so the deformation is maximum where there's no support. Piles are doing a pretty good job, and beams are, yeah, piles and beams are probably doing the best job supporting this trench. Then over here, yeah, most of the deformation is taking place here on the ceiling, which has no shotcrete support. All right, I'm going to just zoom in here because you might notice these weird little axes. All those are is that's the structural elements have their own local coordinate system. And this is important for when assigning a load or a velocity to your structural element. You actually do not use the global coordinate system, which is shown right here, y-x. You use the local coordinate system. The local coordinate system will always be generated automatically for you. But a lot of times if your geometry starts to become very complex, usually in like 3D, when you have like 6 intersecting tunnels, you will start changing the local coordinate system. But in 2D, generally you don't have to. So what I'm showing here is just the system, the node local coordinate system. I can just take it off. All right, so let's see. I think we covered pretty much everything about this simple example. Just real briefly, some of the stuff that will be of interest is right now we're just looking at, so like the pile, we're just looking at its label, a group. Let's maybe take a look at maybe its bending moment. So to do that, anything with force, velocity, displacement, bending moment, we're gonna want to contour it. So just automatically the value defaulted to the displacement of the node. Let's look at, there's a lot of different things. So just keep in mind, generally, they're going to be things for the element itself, like the force in the element, the bending in the element. There's going to be things for the links, which you see right here. So basically, this pile is interacting with the zones, and there's actual force in there. So you can look at that, and it will always say link. So let's just take a look at the moment. And quite as expected, the moments in this pile, let's take off the zone. These are the 2 piles. Because the soil is trying to fall in, it's causing these 2 beams to bend. This is their point of bending, right there and there. A lot of times these are the plots you're showing, these are the plots you're presenting, and then other times you're like, okay, well, we want to know if that element has failed given its properties. The way you determine that is you go to label. It's not a contour. Oops, I'm on zone. I always do this, so I'll start working my attributes, but whatever's highlighted up here is what you're actually working on. So I'm gonna go to my pile. I want to change it to label and state of the element. That's good. So right over here, we'll say no failure. And there's all sorts of other things that have to do with the linking and plastic hinges, which I briefly mentioned, but we won't go into every detail there because we do not have near enough time for that. I'm going to show the nodes. This is still a bug. I don't know why the nodes are behind it. Still have to figure out why. So you might want to find the moment, let's say the moment, and the way you would extract that information is there's going to be a moment for each individual element. It's not like one global moment for the whole pile. And I think the best way would be using fish, which we'll actually talk about next, and that you can access each element. You can write all that data that you see here, moment, force, anything, you can write it to file. You can change it. You can basically do anything you want. That would be my first route to go. The second one is I think you can export, yep, CSV. I think what it will do in this particular, it exports everything in the plot. So I have a feeling it will make a bunch of gibberish for our other elements. So if we just hide the liners, hide the cable beam, I think that's all we got. And now it should, if we say export CSV, it should just export whatever is being contoured. So pile moment, let's see what it does. Check. Yeah. And then the values just remember, so whatever is being exported is not just like the whole moment on the pile. It's going to export the moment for each individual element. So there's the element ID. Then it's giving the position of each end and one value and two value. Okay, yeah. So with that and one and two, yeah, I mean, it's not the prettiest table, but the data is there. So, yeah, that's the way to do it, extract that information. Like I said, easily done in Fish too. And in fact, I would, if I was doing this, I'd do it in Fish because then I can make my table how I want to. That's a quick and dirty way of doing it.